In this video, we will see the proof of limit x tending to 0 for a function sin x divided by x which is equal to 1. So why this is very important to learn and intriguing is that if you have a function sin x divided by x at x equal to 0, this becomes sin 0 divided by 0, which is 0 divided by 0, which is equal to undefined. But the limit is equal to 1 and not undefined. And this is where calculus differs from whatever you have learned, algebra or arithmetic. So why this difference? Because in limit x never becomes 0. Difference between x and 0 is smaller than delta, while delta is the smallest number you can imagine. So that's the classic definition of limit. X never becomes 0. So this sin x divided by x, let me show you from the actual values of sin x and x. So let me first so here we have been using x, so this is x, this is sin x, and this is the ratio. So I wanted to show you actual values of sin s and x as x becomes very small. So we start with 1 and go all the way to 0, and over here is 1, 2, 3, 4, 5, 6, 7, 8. So 10 to the power minus 8. So you see here, when x becomes smaller than this number, the value of sin x and x become same and the ratio becomes 1. But when x becomes 0, then sin x is 0 and the ratio is undefined, is division by 0. So this is, by calculation you can see that for very small values of x, sin x divided by x is equal to 1. So before I show you the proof, there are a few prerequisites that you should know. Number 1 is area of a sector in a circle. So this is a circle and the radius of the circle is r, and we take a sector OPA that makes angle x on the center, and the area of the sector OPA will be half r square and the angle x. And let me show you the proof of this very quickly. You know that area of a circle is pi r square, and you know the angle that it makes at the center is 2 pi. This is angle 2 pi and this is radian. So 2 pi radian is equivalent to pi r square. So 1 radian will be equivalent to pi r square divided by 2 pi, or half r square. Pi gets cancelled. So x radian will be equivalent to half r square x. So this also tells you that our proof will deal with angle in radian. Second is area of a triangle. I'm sure you know this from a long time, that if this is a triangle and this is the height and this is the base, area of the triangle is half HB. H is the height and B is the base. And number 3 is that we'll be dealing with sin x. So if this is P, this is O, this is Q, so sin x will be PQ divided by OP, and 10x will be PQ divided by OQ. So this is a very quick revision. Now we jump into the solution. So this is a quarter circle and this is a unit circle. Means radius is equal to 1. So this is O. We take a point P here, and of interest to us is this angle X, and this point on the circle is A. So this triangle OPA, the area of this triangle will be, if the perpendicular is PQ, half PQ multiplied with OA. So if you look at this triangle, this right hand triangle PQO, so from triangle PQO, sin x is PQ divided by OP. So PQ is OP sin x. So let me put these values here. Area of the triangle OPA is equal to half PQOA, or half OP sin x OA, and OP and OA are both radius, and it's a unit circle, so it's half multiplied with 1 multiplied with sin x multiplied with 1, so equal to half sin x. Now of our interest is, so this is number 1, and now we look at the sector OPA. So the sector OPA I'm drawing in blue is this. So area of the sector OPA is half, this is the radius r square x, and because r is 1, it's a unit circle, is half x. And the third thing is we extend this a little and drop a perpendicular. This is T. So the area OTA is half TA multiplied with OA. So in the triangle OTA, 10x is equal to TA divided by OA. So this area, if we want value of TA, will be 10x OA. So this is the area of OTA is half 10x OA. So we know this is a unit circle, and OA, this is the radius, which is 1. So this is 1, this is 1. You get half 10x. Now let me magnify that area a little so that you see relationship between these three things. So this is my circle. This is OA. This is A. This is the point P. And this is the triangle OPA. Here is our angle X. And then in blue, let me draw the sector. And then in red, let me draw the third triangle. This point is T. So this is in red. This is triangle OTA. Then in yellow is the triangle OPA, and then in blue we have the sector. So from this, I hope it is clear that triangle OPA is smaller than the sector OPA, which is smaller than the triangle OTA. And this is an inequality and this will help us get the expression that we want. Now we put the values of these. So the triangle OPA was half sin x. Sector OPA was half x from here in blue. And the larger triangle OTA is half 10x. All right, these three things we have seen. Area of the triangle OPA, half sin x. Area of the sector, half x. And area of the triangle OTA, half 10x. And we see that OTA is the largest, and after that is the sector, and smaller than that is the triangle. Now you should know the rules of inequality. That's another prerequisite. So half will get cancelled. So sin x is smaller than x, smaller than sin x divided by cos x. And now we divide all the three terms with sin x. We get sin x divided by sin x, x divided by sin x, sin x, cos x, sin x. So what it leaves us, this is 1, this is x sin x, and this becomes 1 by cos x. So we are left with now we invert it. So when we invert, the signs ka direction will change. So cos x, I'm sending the values. So cos x one. So what we did, that if we had a greater than b greater than c, so 1 by c will be greater than, will be, so when you invert, I think let me keep the same form as I have here. So if a is less than b less than c, so 1 by a will be greater than b, 1 by b greater than 1 by c. So the sign changes when you do inversion, 1 by. So so we put cos x here. So sin x by cos x, sin x by x is greater than cos x, which is less than 1. So now we have this, and this is inequality. Now we apply the limit. So you know that limit of cos x as x goes to 0 is 1. And let me show you from the value, the So if you don't believe the limit, I ran the calculation, and you see that as the value of theta goes towards 0, the value of cos goes towards 1. Okay. So now when we apply the limit here, cos x 1, sin x by x, and 1. So you see that the value of sin x is sandwiched between 1 and 1, and it looks a lot like the sandwich theorem of limit. Sandwich theorem of limit. What it is that if you have three functions, such that the relationship is like this, that fx is greater than or equal to gx, which is less than or equal to hx, and if at certain value of x the limit of gx at the same value of x, c, hx is equal to L, this implies that the limit of fx at the same value of x will also be L. So this is that you have fx is sandwiched between gx and hx, so the limit of fx will be the same as limit of gx and hx at certain c. So here you see here that sin x by x is sandwiched between 1 and 1, so that's why limit of x is sandwiched between limit 1, 1. So this is your gx, this is your fx, and this is hx. So you know that limit of a constant is a constant, so this shows that limit of sin x by x is equal to 1. So the key concept of this is coming up with this inequality of this triangle, this sector, and this the triangle, and going through these values. Now intuitively you see here is that edge x will become closer and closer to 0. These 2 points will merge. So these 3 areas in red, then the area of the sector, and the triangle inside, they all will become equal as x gets very close to 0 or p gets very close to a. All right. So that's how we know that this inequality is correct. So I hope you found it useful. Thank you.